All right, moving on to chapter 6 here. Chapter 6 has to do with ionic compounds. Remember that the definition or the differentiation between ionic and covalent, it has to do with how electrons are shared or given. So ionic compounds are those where there's a complete donation of electrons from one thing to the next. Whereas a covalent compound or covalent bond is this sort of equal sharing of electrons. So they're both pulling on the same electron. So we're going to start this chapter with thinking about the electron configuration of ions and ionic compounds. So this is just a natural extension of where we left off in the last set of chapter 5 videos. So these are pretty straightforward. We might as well just do a couple examples. We've got the periodic table here. So let's do sodium first. And let's think about sodium element, so that the actual neutral atom, and then we'll pull an electron off of it because we know that the oxidation state of these group 1A metals tends to be +1. These tend to be +2. These tend to be 0. Way out here, these are -1, -2, -3, etc. So for sodium, let's just write out the full configuration. So we've got 1s2, so 1s1, 1s2, then 2s1, 2, there's 2s2, and then 2p 1, 2, 3, 4, 5, 6, so those are all full, 2p6, and then sodium we drop down to the n equals 3, so that fills up the first half of the 3s orbital. Okay, so let's think about then, if that's the atom, this is the neutral atom, we already know how to do that. But what happens if we allow this thing to ionize, which is what it's going to do. It's going to want to become this +1 state. So we'll say it's -1 electron. Now this is going to be, where does that electron come from? Well, it's pretty straightforward. This becomes 1s2, 2s2, 2p6, and then, of course, we've got this electron hanging way out there in this big shell on its own. That's going to be the easiest thing to remove, so we're going to end up with just this as our closed shell. Conveniently, what does this also look like? Well, if we look back, it is the same as the next closed noble gas configuration. So it ends up being neon with nothing else added onto it. And that's exactly why this ion tends to take the form that it does. This is why the group 1A atoms or elements tend to only lose one electron to become +1. That's because it only takes one to lose to become this nice, happy, stable, full shell configuration of a noble gas. Right? The same could be said for, let's say, chlorine. So let's look at chlorine over on this side. So we're looking at chlorine atom. So chlorine, this is going to have a configuration of 1s2, 2s2, 2p6, 3s2, 3p5, right? Yep, 3p5. So similarly, we know that those ions, the halides or the halogens, tend to want to absorb just one electron and become -1. So this, again, is the neutral atom that's got oxidation state of 0. Let's pop one electron onto this, and what does this become? Well, this is now 1s2, 2s2, 2p6, 3s2, and 3p6, where this electron gets tacked into that empty slot on the 3p orbital. Oh yes, what does this coincidentally look like? It looks exactly like the closed shell for argon, right? We just tacked one electron onto this chlorine, which is the same configuration as argon, which again is exactly why these halides in group 7A tend to want to accept one electron, because all of these atoms, when they become ions, they're making a move to try to become more stable than the element was before. How do you get to stability? Well, you get rid of electrons that are way out in outer shells by themselves, or you fill up a subshell that was almost full before. Those are nice closed shells that have the same electron configuration as the very stable noble gases. And really that's the general premise for how we're going to think about how ions have electron configurations. So what about transition metal ions? It's not so cut and dry. Let's think about iron. So iron has a closed shell configuration. I'll just write up here as argon 4s2 3d6. So if we wanted to create, say, iron 2 plus, we need to drop 2 electrons off this configuration. And in order to do that, it gets a little bit tricky. So the general rule of thumb is that you will remove electrons in making an ion. So again, this is iron 0. This is the neutral form of iron on the periodic table. You're going to remove these 2 electrons from the highest principal quantum number first. That's the general rule of thumb. So if that's the case, and that's because they're the furthest out from the nucleus, then we're going to get rid of, and we're going to snag those 2 electrons right there. So that's going to give us argon 3d6. So we got rid of those 2 4s electrons. What if we want to make iron 3 plus? So again, we're starting with iron 0. So we have argon 4s2 3d6, but now we've got to pop 3 electrons off of this thing. Again, same thing, we're going to start by removing the highest principal quantum number of electrons, but that's not enough, so we're going to have to snag 1 off of this 3d orbital. So that's going to give us argon and then 3d5. So general recap with these transition metals, and really any ions that are going to be formed, you're always going to yank out the highest principal quantum number electron first. If you still need more, then you're going to drop down to the next lowest energy orbital in the configuration that's filled. One other quick example here, let's lump in sort of these anomalous ones as well. So do chromium. So chromium, remember, we did this as an example before. It's in this first set of transition metal series, and it's in this D4 set. And we said that actually the ones that are in this D4 set, they'd rather be D5. They'd rather have a half-filled d orbital subshell, which means that it's going to steal one of its electrons from this 4s state. And so the actual ground state electron configuration for chromium metal, chromium 0, is going to be argon 4s1 3d5. That should look familiar from a previous video in chapter 5. So what happens then if we want to make this, let's say, chromium 3? So let's snag 3 electrons off of this. Well, we're going to start by grabbing, again, the highest principal quantum number. So we're going to zap that thing, but then we still need to grab 2 from here. So this is going to give us argon and then 3d3.